This
So
conference will now be recorded.
we had last class we had started with little bit of dimension analysis, and that day we had learned what is called dimension, etc. So today we'll see what is called dimension analysis and how it helps us in correcting some physical relation, some physical equations, and how it helps us to convert one unit to another, and how to derive physical quantities using dimension analysis. So today's lesson is dimension analysis. So what is dimension analysis? Method of studying a physical phenomenon on the basis of dimensions is called dimension analysis. Okay, just a minute. Yeah, now. Yeah, so the method of studying a physical phenomenon, okay, on the basis of its dimension is called dimension analysis. We'll very soon learn what this definition is saying us. And basically, this is very important, okay? This is very important. Applications of dimension analysis. So, what does like this dimension analysis do for us? It helps us to convert one quantity from one unit system to another unit system. Okay, it can help us to convert. We'll take up examples slowly. Let me first tell you what are the applications of dimension analysis in our physics. The second thing is it helps us to check the correctness of any physical equation. Some equation may be given. You have to check whether that equation is really correct. So that can be done by dimension analysis. Then we can derive even physical quantities. We can derive physical quantities in terms of their fundamental dimensions. Okay, and that is also that also can be done by the help of dimension analysis. Okay, it must be sounding very much abstract for you what I'm talking. Let me take examples of this like individual applications, and then it will be very much vivid for you. So let us take the first one, how we can uh, convert a physical quantity from one unit to another unit. So conversion of units, and actually it is based on the fact that any quantity, magnitude of any physical quantity does not change whatever may be the unit system. Suppose I have certain physical quantity that is q, okay, certain physical quantity q, I have to measure that, and I can measure that in two different unit systems. Suppose u1 unit system, okay, and u2 unit systems. So these are actually two different unit system, like you have SI system, FPS, CGS, etc. So I'm just measuring a quantity q in two different unit systems. Suppose, see, whatever may be the unit system, if I say one, suppose this is 1 kg, 1 kg of rice, 1 kg of rice, does it change? Does the quantity change? If I measure that in CGS or SI, doesn't matter. It is always 1 kg of rice. But in case of CGS, we say 1000 gram. And in case of SI, we say 1 kg. That's the difference. Okay, that's the difference. Otherwise, nothing. So look, we will not take specific unit system. We'll take in general. So I'm taking U1 is one unit system, U2 is another unit system. Obviously, when I say 1 kg rice in SI, so this is 1000 gram in CGS, right? So you can see 1 into 1000, then you get the other unit. Okay. Similarly, if I want to write the quantity, okay, if I write if I want to write the quantity Q, so in one unit system, suppose I say N1 is the multiplicative factor into U1. In another unit system, the same quantity can be written as some other multiplicative factor into U2. Okay, so this is how it is written over here. So what is the basic thing is that the quantity does not change. Magnitude of the quantity does not change with the unit system. Okay, so it is all right. So in any unit system, there are three fundamental physical quantities. That is, one is mass, denoted by capital M. Okay, mass, capital M. Then length, denoted by capital L, and time. So these are the fundamental unit systems. Sorry, yes, fundamental quantities, physical quantities in any unit system. Okay, these are fundamental quantities has been taken internationally or globally to be the basis of any unit systems. So what I can do, I can take in unit system U1, I can take this as, see, the physical entities in U1. I can think these are M1. In this unit system U1, mass is M1, length is L1, and time is T1. Similarly, I can take in unit system 2, the corresponding quantities are M2, then L2, and T2. Okay, these are the corresponding quantities. Okay, now see, as I said, these physical quantities, they have to be uh, like whatever unit system it may be, it will be the same. Now here is coming the dimension analysis. Okay, here the dimension analysis is coming. I'll just tell you what you have to do after that. We have to write the dimensional expression for the physical quantity in that particular unit system. Dimensional uh, equation also I can say. So I'll write U1 uh, is equal to U1 is equal to M1 to the power A. This is, see, this power is the dimension. Okay, power is the dimension, and then you must be uh, writing in square bracket, inside a square bracket. Okay, sometimes all the quantities can be written in the same square bracket also. I'm just doing that only. So m to the power 1, L1 to the power B, and T1 to the power C. Okay, in unit system U1. So U1, then I can get Q is equal to N1 U1. That means I can write n1 into this m1 whole power to the power a, l1 to the power b, and t1 to the power c. Okay. In a similar manner, I can write in terms of the second unit system or the other unit system u2. So this can be written as n to u2, where this is n2 and in a square bracket m2 to the power dimension same dimension and t1 to the power c. Look, this dimension, because we know the dimensional expression, so this a1 a b c, these are same because any physical quantity has the same dimension in any unit system. So that's why the dimensions are actually same. You might be thinking, sir, why you have taken in this case also, like you have taken m2 m1 m2 l1 l2 t1 t2, why don't you take a1 b1 c1 and a2 b2 c2? I'll tell you one thing, that it, for any physical entities or quantities, dimension does not change in any unit system. Dimension does not change. Okay. So that's why I'm just writing that. Now what I'll do, because these are both q, the same quantity, I can write in terms of equation now. Okay, so I think, yeah, here n1 multiplied. Okay, so n1 m, m1 to the power a l1 to the power b t1 to the power c, like that. And similarly on the other side, I'll write n2 to into m2 to m2 to the power a, l2 to the power b, t2 to the power c. Okay, now I have to calculate what is this factor. Suppose I know this, I know n1, I know the values of a b c, then I can actually do the conversion. I'll take real example. Let me write the in general case. So n2 will be equal to n1 multiplied. See, if I just take it in the other side, so it will be m1 by m2 to the power a. Then you will have l1 to this, and you will have t1 by t2 to the power c. This is your whole equation. And look, I'll be, let me just clean this portion. So I'll be using this equation to convert any physical quantity from one unit system to another unit system. Okay, let me uh, take one example. So let me just clean this portion first. So I write this equation somewhere in the top. So what I have got, n2 is equal to n1 into and then t1 by t2 to the power c. This is the thing. Okay, now I can just use this formula, use this dimensional formula to convert a physical quantity from one unit system to another. Let me take one simple example. Suppose work done. So what is the, you need to know, first of all, see, in this case you need to know what is ABC. That means you need to know what is the dimension of work done. So I know the dimension of work done will be force, see, dimension of force into displacement. Okay, displacement. So dimension of force, by now you might be knowing, dimension of force is m l t to the power minus 2. Okay, and you have a dimension of this displacement as l. So you have finally the dimension of work done is m L square T to the power minus 2. So if I write this quantity work done, so this as Q. So you know the dimension. See, you know the dimension. Now what I'll do, I have to convert 1 joule, 1 joule to how much, okay, to how much arg, okay, sorry, ERGS, how much ERGS args, ERG, okay, how much arg. So that means we are just going to convert work done, the unit of work done or unit of work from SI unit to CGS unit. So there is a factor you know already, you might be knowing. Now I let me think I don't know. So in this, when you are asked to do this, you have to recognize which one is M1, M2, and like which one is M1, L1, and T1, and which one is L2, M2, and T2. See, this I have to calculate. So let us take this N2 factor. I have to calculate. I know N1 is 1. Okay, I know. And this joule means I see in joule M1. So this you have to take M1, which is given. 1 joule means it is given. So M1 in this case is 1 kg, which is actually 100 gram. Then you have L1, this is 1 meter, which is 10 to the power 2 centimeter. Okay. Then time is same for both the things. So it is 1 second. So 1 second. So now look, uh, I'll be putting my things in this formula. So here I know, see here I'll write down what is A. A means 1, B means 2, and C means minus 2 from this dimensional formula. So m to the power A, L to the power B, and T to the power C. So C is minus 2, and B is plus 2, and A is 1. So that is what we have got from this dimensional formula. Now I am just converting it by the use of the formula which I have written on the top. Look here, into, I have to find out the multiplicative factor in CGS. So you look here, M1 by M2, okay, to the power A. Then you have L1 by L2 to the power B into T1 to the power T1 by T2 to the power C. This you have. Okay. All right. So N1 is 1 joule means N1 is 1. So I can write this as N1. See, M1 means it is in the SI unit system. So I'll write 100 gram. In, see, M2 is CGS unit system. So gram, that is actually 1 gram in CGS unit. Okay. So this is to the power. A means what? To the power 1. Because from the dimensional formula we had got A, B, C, etc. So now L1 by L2. So L1 is in SI. So 1 meter means 100 centimeter, and this is 1 centimeter. So if I write this is centimeter, this is also centimeter, and you have, okay, you have B means square. Okay, you have B means square. B means 2. So see from here. Okay. If you are following, then you can understand how I have written A, B, C, like A, B, C, 1, 2, and minus 2. And see, this is actually T by T1 by T, both case, both unit system T is same. So this is 1 over, okay. So 1 over 1 to the power 10 to the power 1 to the power, you have this one 1 to the power minus 2. So doesn't matter, 1 to the power minus 2 means 1 by 1 square. So that is also 1. So let us see what I get from here. See this, I get 10 to the power 2, sorry, 10 to the power 3. This gram, they both cancels out. The centimeter cancels out. You get again here 10 to the power 2 and whole to the power 2. So 10 to the power 4, and here you get 1. So what you get is actually 10 to the power 7. Okay. So 10 to the power 7. N2 means 10 to the power 7. Okay. So this is how you can find out the unit. So you can get 1 joule means 10 to the power 7 arg. 10 to the power 7 args. Okay. 10 to the power 7 args. So this is what the way. I'll take one more simple example so that it will be again uh, more clear, or maybe you can do yourself also. I can help you uh, to apply this dimensional uh, analysis to find out. See, maybe I'll just tell you one thing. Uh, okay, so since I'm not able to see you, I'll do the things. You can just verify. Deepa, uh, now we'll be using dimensional analysis. That means this formula to find out what is 1 Newton, okay, is equal to in cgs. Okay, that means dyne. How much is the dyne? Okay, 1 Newton means how much dyne. Look what we'll do. So this is Newton means equation of, again this is actually Newton means force. So force has dimension m l t to the power minus 2. Okay, this is the dimensional formula. Okay, for force. Now we'll be using this. See, n2 is equal to, see, 1 Newton means n1 is equal to 1. I'm not going to write that. So look, m1 by m2. Here also, see, okay, I'll just do one thing. Let me just take the opposite so that you can get a nice flavor of that. Okay, let me write in opposite. That means I have to see 1 dyne is equal to how much. 1 dyne means how much? How much is the Newton? Okay, Newton, or simply capital N. Okay, how much Newton it is. So see, when I am writing this N2, that means I am just finding out in the second unit system. Okay, and look, this is to the power, this is L is equal to, M is equal to 1. Again L means L1 by L2. This is again 1. So to the power 1 into T1 to the power T2, which is to the power minus 2. All right. Now look, in this I have to write in CGS, and this is actually SI. So I have to write this quantity CGS in terms of SI. That means, so 1 gram means, see, 1 gram means 10 to the power minus 3 kg. This is what I have to write now. And in this M2 I have to write 1 kg. Okay, whole to the power 1. Now look, this L1 I have to write 10 to the power minus 3. Sorry, 10 to the power minus 2 centimeter means 1 meter. Okay, this is in CGS. See, 1, now 1 actually with subscript 1, this is CGS, and with the subscript 2, this is actually SI unit. That's why I'm just going to write that. Okay, in, so here you might be thinking, sir, when I take this ratio, which one to take, like in which unit? I'll tell you in which unit system you are going. You have to convert the quantity to that unit. Like, see, I'm writing here, instead of writing, see, 1 gram, I should have written 1 gram in the numerator, and in the denominator I should have written uh, 1 kg. If I would have given, I would have been given the opposite way. Since I'm going to SI unit, you have to take M1, M2, M3, like M1, L1, and T1 all in SI unit. Okay, so this is actually this much meter. 1 centimeter means this much meter, and L2 you know already in meter, and this has T1 by T2 in both unit system T1 and T2. Magnitude of T1 and T2 are same, so it will be giving only 1. Look now what I get from here. So I get from here is see kg goes up, meter goes up. You get only a factor or a number. This is 10 to the power minus 5. Look, what you get is n2 is actually 10 to the power 5 minus 5. 10 to the power minus 5. That means what? That means what? You are just calculating in unit 2. So this is a Newton. Okay. So you look here, 1 dyne is equal to 10 to the power minus 5 Newton. Okay, 10 to the power minus 5 Newton. So 1 dyne is equal to 10 to the power minus 5 down Newton. I'll tell you one more thing here, like once more this thing. When I take ratio of M1 by M2 or L1 by L2, which one to write in gram, which one to write in kg, and like whether we should write both of them kg or both of them gram, that depends. So that depends in which unit you are going, you are taking your, like in which unit you are going to calculate this factor. If it is in SI unit you are going to make calculate the factor, then M1 by M2 this you have to take both in SI unit. Okay, all right. So this is how, look, we can use the dimension analysis to find out the factor with which you can multiply the quantity and get the conversion done. Conversion means from one unit system to another unit system. Okay, like here I had taken two examples, one for work done, that is so in SI to CGS, and in this case I have taken how to convert the quantity force from CGS unit to SI unit. Just a minute. So I hope you have understood how to apply this dimension analysis to convert a quantity from one unit system to another. I'll just go to the second application, how to check the correctness of the uh, physical equation. Okay, so there is a principle called homogeneity in dimension. What does that mean? Uh, to check the correctness of any physical equation. Okay, any physical equation, you have to use the principle of homogeneity of dimensions. Look here, principle of homogeneity of dimensions. What is that? Like, yeah. So the principle of homogeneity of dimension states that any physical equation will be dimensionally correct if the dimensions of all terms occurring on both sides of the equations are the same. Okay, according to this principle, you can add two physical quantities which are having similar dimension, like length can be added with length or subtracted from length. Velocity can be added or subtracted from, like added to or subtracted from velocity only. You cannot do velocity addition with acceleration. Okay, this cannot be done. This is not possible. Okay, this is not possible. Okay, so this is called homogeneity of uh, dimensions. So in any equation, so what is this saying? That in any equations, suppose I write force is equal to mass into acceleration. Okay, so I have to see this force left hand side and right hand side both has to be in the same dimension. Look, if I say force, I know m l t to the power minus 2. Obviously this is not an equation, this is dimensional equation only. So, and here you look m, and this is acceleration means l t to the power minus 2. All right, so this is not a correct equation. I'll take one physical equation. Let me tell you. See, you might be aware of this equation in kinematics, that x is equal to displacement is equal to initial displacement plus the initial velocity into the time plus half acceleration into t square, the time square, will give you the displacement of a particle at any time t. Okay, this is the equation. It will give you the displacement of any particle at any instant of time. Let me, or after interval of time also it can give. So in this case, what you have, see, I have x, then I have x0. I have, see, x in the left hand side, x0, then this is velocity, okay, into t plus half acceleration into t square. So whatever quantity you see in the right hand side and whatever quantity you see in the left hand side, both, actually both sides have to have the same dimension. Let us take the dimension of x. So what is the dimension of x? This is having a dimension of length. All right, l to the power 1 also I can write. So what about x0? The same thing, this also has unit of length only. Okay, unit of length. What about this thing? This also, because it is added with x0, which is having a dimension of length, so v into t or u into t must be having a dimension of u, t must be having a dimension of length. We'll verify that. We will verify that. Then this acceleration half t square, so this any constant does not carry any dimension. Any constant, algebraic constant, cannot carry any dimension. Okay, so look, this a and t square, this also has to have dimension of length. Then only this equation will be dimensionally correct or it will be perfectly correct. All right, look, I'll just try to do the dimension analysis in this case. So for doing this dimension analysis, obviously you should have prior knowledge to the quantities which I have written over here in this equation, like how dimensionally they are related to one another. So that you have to, and each individual quantity, dimension of each individual quantities in the equation you need to know. Suppose I know dimension of x is length, okay, dimension of length. Now let us see u and t. What is the dimension of this? So look, u means velocity, that means length by time, so l t to the power minus 1, and this is again a t. T means again it has dimension of time, so I can write this as l t to the power minus 2. Okay, so look, oh, I'm sorry, not minus 2, this has plus 1. Okay, so this will be finally t to the power 0. Okay, that's how t to the power 0 means 1, so it is having a dimension of l. So this is t to the power plus 1, so this is t to the power plus 1, this is t to the power minus 1. So according to the formula for index, so it will be t to the power 0. So l t to the power 0, that means it has dimension of length. Now we'll take the final one, that is 8 square. So 8 square also we have to prove that it has a dimension of length only. So as I said, 8 square, half 8 square, this is a quantity algebraic constant. So this is dimensionless. This is dimensionless. Okay. So only dimension will be here for A and for the square. Okay. Look, this A means acceleration, velocity by time. Velocity we have already seen, L to the power minus 1, by time again, then L to the power minus 2, and here it is again T to the power T square. So these two together will give you again unit of length only. So I hope you have understood how we have seen that. So both side the dimension was of length, okay, was of length. Okay. So this is how you can find out whether any quantity is dimensional, like any physical equations are correct or wrong. Actually, we can take one simple example. Uh, one more example maybe. Okay, let us take one example, one more example. We know half mv square is equal to, so this is kinetic energy is equal to mgh. It is actually when you just drop any mass, any object of mass m from rest. When it touches the ground, just before that, suppose it was at h height, from it is actually left from h height, just before hitting the ground, it will have the highest velocity v, and that's how we get actually here the whole potential energy mgh, and here will be the uh, total kinetic energy, or the whole potential energy will be converted to kinetic energy, so which is given by this relationship. Okay, we have to see whether these equations are correct or not. So look, I'll take, see, this is dimensionless, I'll take this two dimensions. So dimension of m v square, this side. So m is already having dimension of m. V square means velocity square. Velocity we know L t to the power minus 2 and square of it. Okay. So what we get is m L square t to the power minus 4. Okay. T to the power minus 4. So this is the dimension I get. I need to check what is the dimension in the right hand side, mgh. Let us see m, g, and h. Okay, m has mass, h has length, and see, g means one type of acceleration, so that will be L t to the power minus 2. Okay, half m v square. I'm sorry, it is actually v means not t to the power minus 2, it is t to the power minus 1, L t to the power minus 1, because velocity is distance by time. Okay, so this distance is L and time is t, so L by t to the power minus, L t to the power minus 1. I'm sorry, it was wrongly written. So L m L to the power t to the power minus 1, the whole square of that will give you t to the power minus 2. Okay, whole to the power, that will give you 10 to the power minus 2. So look, in this mgh also you get ml square t to the power minus 2. So this equation is perfectly correct. Half mv square is equal to mgh is correct equation. Okay, all right. So this is the thing. So I have given quizzes for like from this chapter, where you can get many such numerical problems. You can just solve just by applying dimension analysis. Okay, So I'll just go to the next part of today's topic, that is derive a relationship between physical quantities. I'll directly take one example. Suppose you have a simple pendulum. Okay, pendulum. Okay, you have to find out the time period of pendulum. You have to write exactly what is the expression for this uh, derived mathematical expression. Actually, here we are deriving mathematical expressions for time period, okay, by dimension analysis. So how to do that? See, in this case, you should have some prior knowledge. What is that prior knowledge? That you need to know. Suppose if I write kinetic energy, so you know it depends on mass, okay, as well as velocity. Kinetic energy depends on mass and velocity. So this is how you need to know. When I say time period of a simple pendulum, then you must be knowing on which quantity, physical quantities, fundamental physical quantities, this time period depend on. Okay? If I say pressure, I know it depends on force and area. Okay, this is how you need to know. If I say time period, then this time period is related to which physical quantities. Okay, actually, for a pendulum, time period depends on length of the pendulum, length of the string. If I draw the pendulum, it is something like this. Okay, so this is length of the string. This is L. Okay, from the fixed point to the bob, center of the bob. That is the length. So it depends on length of the string. It depends on uh, the acceleration, gravitational acceleration g at that particular place. Okay, at that particular place. So you need to know this kind of fundamental knowledge or prior knowledge, like to which quantities it is related to. Now see, you have to write in terms of dimension. See, k, I'll take this is a constant and it is dimensionless. I can write in any equation like that. Dimensionless quantity. And I have L. I'll take L to the power x. Sorry, L to the power x, and L to the power x and g to the power y. Okay, I'll just take this thing. Okay, so I'll write dimensionally. See, this time period, I can write dimensionally m to the power 0. That means it does not depend on m, or dimension of m is 0 for time. L t to the power 0 and t to the power 1. This will give you the dimension of time. So k is dimensionless quantity. So I'm not going to write that. So this is L to the power x, and this is g means this is L t to the power minus 2, this whole to the power y. Okay, this is the thing. Now I'll just solve. This is L x plus y, then it is t to the power minus 2 into y. Okay, now look, I'll just take the, like, I'll just compare from both sides, left and right side. Sorry, this is plus. So see, L has 0 power from both, so I can write comparing left and right hand side, x plus y is equal to 0. That means, okay, yes. So x plus y is equal to 0, 1 equation we have got. So x will be to minus y. And look, 2y, see this 2y minus 2y is equal to 1. So y will be actually minus half. Okay, minus half. So just by comparing both sides, what we have got is, see, x is equal to minus y we have got, and y is equal to we have got minus half. That means you have x is equal to plus half and y is equal to minus half. So this is the dimension. So I'll write that here. I'll write in this equation, I'll write it here. So t is equal to, so this k was found to be 2 pi. And look, this is to the power half, and this g is to the power minus half. If I write it in our known format of root over, half means root over, minus half means 1 by root over, okay, reciprocal of the root over, square root. So I can write this as 2 pi root under root L and divided by under root G, which I can write in compact format, root over L by G. So this is the time period, like formula for the time period or expression for the time period of a simple pendulum. Okay, or okay, so this is for a simple pendulum. So what we get, time period, see, I'm deriving relationship between physical entities. See here, physical entities length and acceleration due to gravity. So what is the relation between time period, length of the string or length of the pendulum, and the local uh, acceleration, constant of acceleration due to gravity. So this is what the relation is, root over L by G. So this is how dimension analysis will help you to find out the relationship between physical entities. Okay, so we can actually derive many such uh, formulas in this way, like just by using dimensional uh, analysis. Okay, I'll just take you through one simple example. Now we'll just apply uh, this dimensional analysis just to solve a simple problem. Since we have got another 5 minutes, we'll just discuss it. We'll just take one example. Suppose uh, so there is a problem here. uh, See, you might be aware of this equation from your chemistry, and also in 12th 11th standard we have this thermodynamics, where we will be learning, this is an equation, uh, this is called equation of state for real gas. Okay, this is an equation of state for real gas or van der Waals gas. So you have to find out the dimension of A and B. What is the dimension of A and dimension of B? You have to use your knowledge of dimension analysis. So look, in this case, when I have added this quantity with P. P is pressure. I'll tell you P is pressure. This V is volume. This R is universal constant, that is constant, but that also has a dimension. Okay, that so universal gas constant, gas constant, and this time, this is actually absolute temperature. So here you have to find out the dimension of B. Suppose let us see dimension of B. See, the dimension of B is very simple because it is actually subtracted from the volume. So we have learned that any subtraction or addition can be done for the quantities which have similar dimensions. So this B will be having a dimension of volume itself. So dimension of volume means L to the power 3. So this has simple dimension L to the power 3. Okay. All right. Now I have to find the dimension of this. So since this is a pressure, so this quantity, this whole quantity also has to be having dimension of pressure only. So if this has to be dimension of pressure, see this V is volume. So look this thing. This is, let us write. I have to find out A by V square. This is actually a dimension of pressure. So pressure means what? So let us see. See, I don't know the dimension of A. I'll just keep it there. I know dimension of pressure. I know the dimension of V square. V square means volume. So I know pressure means force per unit area. Okay, dimension of that, and this is dimension L to the power, see, 3 to the power 2. That means L to the power 6. And this you have m L t to the power minus 2. So this L goes off. So 1 L will come up with a minus power. So m L to the power minus 1. So because this is m L t to the power minus 2, so this will be t to the power minus 2. So now you multiply this with L to the power 6, and if you simplify, what you get is actually m to the power 1, L to the power 5, and t to the power minus 2. This will be the dimension of A. So A has got a dimension m to the power 1, L to the power 5, and t to the power minus 2. So this is how you have to use your dimension analysis to find out dimensions of various quantities when you have been given in a equation. Okay. See, if I just tell one thing, if I say anything, suppose let me just take one more example of exponential. Uh, just a minute. Okay, otherwise I'll just stop it here. Uh, you might be getting our quiz questions on this chapter. I have already prepared those and sent it to Guna madam. So maybe in our website you will get very soon. So just go and practice some of these problems, some quizzes. If you can, then you will be uh, like you will be able to understand, and your knowledge will be more firm. Okay. So with this I'll stop here, Deepa. If you have any doubt, any query, any question, you can ask me for 2-3 minutes. Otherwise, I don't have anything more to say today. Okay, Deepa, you have any question for me? I didn't get you. Do you say yes or no?
No, sir.
Okay. So, do you understand everything what I taught? All right. You just read your textbook now. I think you will be able to understand. I'll stop it here for today. We'll meet again
Okay.
on Thursday with new chapter. So with this, we have completed this chapter, units and measurements. We'll be starting the second chapter hereafter. On Thursday, we'll start the new chapter. I think that will be motion in a straight line, maybe. Okay. So we'll meet again on Thursday. See you, Deepa. Bye.